Welcome. In the last lecture, so we have to study what is a ordinary simultaneous differential equation. So an equation of the form dx upon p is equal to dy upon q is equal to dz upon r. Then the differential where p, q, r are the functions of x, y, z. Then dx upon p, dy upon q is equal to dz upon r. This differential equation is called ordinary simultaneous differential equation. And how to obtain the ordinary simultaneous differential equation? We take two simple first degree differential equation, that is p1 dx plus p2 dy plus p1 dx plus q1 dy plus q1 r1 dz is equal to 0, and we take another simple differential equation first order first degree, so that is p2 dx plus q2 dy plus r2 dz is equal to 0, and we solve simultaneously both the two equation at a time. Then we get dx upon p, so that is dx upon p is equal to dy upon q is equal to dz upon r. So this differential equation is called simultaneous differential equation, and we discussed how to solve the this differential equation. So there are two cases, one particular case and another is general case. So what is a particular case? Means we take any two fractions of these equations. First two fractions are, second two fractions are, first and three, and so on. Taking two fractions and one variable out of x, y, z is absent, and then solve the two fractions. We get one part of the complete solution. We take for the another solution, we take another two fractions and also neglect or also delete one variable and also obtain the solution, and those two solutions taken together is the complete solution. This is a general case. Okay, so what is the particular case? What is the particular case? So if we unable to solve this differential equation by using the method such as general case, then we take set of multipliers element, and we multiplying element to dx dy dz also and pqr, and then adding them. If denominator is 0, then what happen? So we see in the last lecture how to obtain the solution of this differential equation. So we take here also examples. So solve dx upon x into y minus 8. So dy upon y into z minus x. So dz upon z into x minus y. So this is the, where p is this, q is this, r is this. So this is ordinary simultaneous differential equation. So how to solve this differential equation? If we take any two fractions, so this is impossible to delete one of the variable. So we adopt here. So that is a particular case. So method. So let us choose the set of multipliers. Set of multipliers 1 1 1. So we take this set 1 1 1. So each fraction each fractions is equal to so multiplying 1 to this, also 1 to this, so that is dx. Multiplying this one to this and to this, multiplying 1 by this, and adding numerator and denominator. So dx plus dy plus dz divided by x into y minus z plus y into z minus x plus z into x minus y. Okay, so those multiplies in our hands, so that is our choice. We choose that multiplier such that denominator becomes 0. Denominator becomes 0. Okay. So this is equal to what? So that is dx plus dy plus dz divided by what? So dx plus dy plus dz divided by, so this xy, so this is minus xy, minus xz, then this is plus xz. So all those terms cancel here, so we get 0 at the denominator. So this implies that therefore dx plus dy plus dz is equal to 0. Okay. So on integration. So what happened? Taking integration of this equation. So integration of this. So integration of dx is x plus integration of dy is y plus integration of dz is z. So is equal to integrating constant 1. So this is one part of the solution. This is one component of the solution. This is one part of the complete solution. Okay. So what is the another part? So what is the another component of the solution, complete solutions? So we choose another set of multipliers. Let us choose another set of multipliers. So what is the set of multipliers? So that is very simple here. So what is another set here? We choose. So if we choose such set, then denominator automatically get 0. So the sets is 1 upon x, 1 upon y, and 1 upon z. So that. So what is each fraction? Each fraction means this fraction is equal to this fraction is equal to this fraction is equal to this fraction. So each fraction is equal to. Each fractions is equal to. What happened? So multiplying this 1 upon x to numerator and denominator, 1 by y to numerator and denominator, 1 by z to numerator and denominator, adding them. So that is 1 upon x dx plus 1 upon y dy plus 1 upon z dz divided by. So if we multiplying 1 upon x to this, so x get cancelled, so y minus z. Multiplying by 1 upon y, we get z minus x. Multiplying by 1 by z, so we get x minus y. So what is this? Denominator is 0 here. So this implies that 1 upon x dx plus 1 upon y dy plus 1 upon z dz divided by 0. So this is 0. So this implies that therefore 1 upon x dx plus 1 upon y dy plus 1 upon z dz is equal to 0. Is equal to 0. Then we integrate this equation. So what is the integration of this? On integration. What happened on integration? On integration. So what happened? Integration of this is log x plus log y plus log z is equal to integrating constant log c2. Okay? Log c2. Then what happened? So this implies that log xyz, logarithmic rule. So this is log c2. So therefore xyz is equal to c2, taking antilog of both sides. So this is 2. So this is another part of or another component of the complete solution. So this is another component of the complete solution. Okay. So these two solutions taken together, the solution 1 and 2, the solution 1 and 2 taken together is complete solution. Complete solution. Okay. So this is a very simple method to finding the solution of ordinary simultaneous differential equation. Okay. So we take another example here. So solve the differential equation. So each example is different. So if we unable to solve that differential equations, so you make many fractions, infinite fractions, and solve the differential equations. So we take example. We take example. So solve differential equation. Dx upon z, dy upon minus z. Then z square plus x plus y bracket square. So solve this differential equation. Okay. So how to solve this differential equation? Okay. So taking two fractions. So solution is what? Taking first two fractions. So what are the fractions here? Dx upon z is equal to dy upon minus z. Okay, this fraction and this fractions. So this implies that the z variable is a cancelled, absent. So that is dx is equal to minus dy. So this implies that dx plus dy is equal to 0. So on integration of the taking integration of this, so what happened? So this is on integration. On integration we get integration of this is x plus y is equal to integrating constant, so that is 1. So this is one component of the complete solution. This is one part of the complete solution. Okay. So now we take another two fractions. So if we take this fraction or this fraction, we take this fraction or this fraction. So let's take last two fractions, taking last two fractions. So what happened here? So last two fractions are, so dy upon minus z is equal to dz upon z square plus x plus y bracket square. Okay. So there are three variables. We take last two fractions, but this is difficult to absent one of the variable from variable x, y, z. So this is difficult one. But there is a clue, very simple clue. So put x plus y is equal to c1 there. So this implies that what happened? So dz upon minus z is equal to dz upon z square plus x plus y is what? c1. So that is c1 square. So it is very easy to solve this differential equation. We can take integration. Okay. So what happened here? So on integration we get, on integration, just we write simply this equation in the form here. So that is dz is equal to, dy. So that is dy is equal to what? Minus z. Separate here variables. So dy as it is, minus z is there. So dz upon z square plus c square, z square plus c square. So now we can take integration of this equation because the variables are separate here. So on integration, what happened? On integration of dy is 1. So what is the integration of this? So integration of this is minus 1 half log of z square plus c square. Okay, log of z square plus c square plus integrating constant something c2. This is equation number 2. So how to obtain this integration? Because derivative of this, what is the derivative of this? So that is 1 upon z square plus c square into derivative of z square plus c square is 2z. 2 get cancelled. Okay. So this is the integration. So this is another part of the complete solution. This is another part of the complete solution here. So these two solutions, 1 and 2, the two solutions 1 and 2 taking together is the complete solution. Hence the example. So this is very simple examples. Okay, it's a very simple examples. So we take another example. Simple examples. So solve x square minus y square minus z square, okay, dx upon, then dy upon 2xy, then dz upon 2xz, okay. So this is the ordinary simultaneous differential equations. Okay, how to solve this differential equation solution? So taking last two fractions, it is better to take last two fractions first. Taking last two fractions, so that is dy upon 2xy is equal to dz upon 2xz. dy upon 2xy is equal to dz upon 2xz. So what happened here? So 2x get cancelled, x is removed there. So that is, what is remaining implies that, so dy upon y is equal to what? dz upon z. So variable are separate. So it is easy to take integration. So on integration what? So on integration, what is the integration? So this is log y is equal to log z, integration of this is plus log c2, then what happened? So therefore log y is equal to log z c2, log z plus log c2 is equal to log z c2. So this implies that y is equal to z c2. So this is equation number 1, and this is one component of this complete solution. This is the one of the component of the complete solution here. So okay, this is one part of the complete solutions. So now what is the next part? So what is the next part? So that is difficult. If we take these two fractions, then we get a solution. So if we take first and third fraction, so that is difficult to solve this equation. If we take these two fractions, then also difficult to solve this differential equation. So how to solve this differential equation? So we solve first part by using general case. Then what is the next part? So we take particular case. So let us choose the set of multipliers. You can do also such. Okay, let us choose the set of multipliers. So to find the solution, so another part. So now let us choose the set of multipliers. Choose the multipliers or just what happened here? Just remember. So we are taking here multipliers to, so we don't take, so take multipliers and denominator becomes 0. So what are doing here? So we take multipliers. So these are 3 fractions. And difficult to solve this differential equation. So what are doing here? What are doing here? So we make another fractions. So it is possible to make infinite fractions and then 2 fractions of them and solve this differential equation. So why you are taking multipliers to making 0? No. Simply, if it is possible, then okay. But there is, I don't know, is it possible or not. But it is better to take, to make another fractions and then solve this differential equation. So let us choose the multipliers xyz, multiply xyz such that, so what happened here? So this equal to, so each fractions is equal to, what happened? Multiplying this x, so x dx divided by then x into x square minus y square minus z square is equal to plus y dy plus, what happened? Multiplying y to this, to xy square, multiplying to this by z dz plus 2xz square. But this is not a 0. Okay? So this is equal to x dx plus y dy plus z dz after simplification. So we get here, so x into bracket x square plus y square plus z square. After simplification, it is very simple. So this is not a 0. So we make another fractions here. So now we have to solve this. So taking fractions, which fractions? These fractions or these fractions, you take any. So these fractions dy upon 2xy, dy upon 2xy is equal to, this fraction is, each fraction is equal to this. So this is equal to this, equal to this, equal to this. So we take this fraction is equal to this fractions. X dx plus y dy plus z dz divided by x into bracket x square plus y square plus z square. So very simple. Then what happened? X get cancelled. Okay, so this can be written as dy upon y, 2 taking here, 2 into bracket x dx plus y dy plus z dz divided by what? X cancel, taking 2 here. So that is x square plus y square plus z square. And this is a very simple. Why simple? If you take integration, we get solution. So on integration. What is the integration? On integration, so what is the integration of this is log y. What is the integration of this is log of x square plus y square plus z square plus integrating constant log C2. Log C2. Then what is the solution? So y is equal to what happened? So log y is equal to log of x square plus y square plus z square into C2. Okay. So then y is equal to what? X square plus y square plus z square into C2. So this is another component of the complete solution. So what happened? This is a solution 1. This is a solution 2. These two solutions taken together is the complete solution. Okay. So each example have a different method. So it depends on example. So there is no such method, fixed method to solve this differential equation. First you see example and you decide how to solve this differential equation. So you make many fractions, then solve. So each student have different solution, because anybody have taking another fractions, another multipliers. So you get another solution. But finally, so you taking this two solution together is the complete solution. So how to solve? You solve more example, then you get the idea to solve the ordinary simultaneous differential equation, because there is no fixed method to solve this differential equation. Okay, thank you.